Hello and welcome to the fourth episode of my free CCNA complete course. Today we'll be discussing about fundamentals of WAN and IP routing. Before we start, please subscribe to my channel to get the latest updates on the videos that I'm posting. WAN or Wide Area Network is a large network of information that is not tied to a single geographical location. It facilitates communication and sharing of information between devices which are not present in a single geographical location, usually through a WAN provider, or in normal terms like an ISP or a TSP, that is an internet service provider or a telecom service provider. The WAN technologies that we'll be discussing today refers to the physical standards, which is the layer 1, and the data link protocols that use to make this connectivity possible, that is the layer 2, between the two endpoints. A simple WAN connectivity like this, where two LANs are connected by router 1 and router 2 with the help of a WAN connection. Here, WAN is represented by a crooked line which represents a leased line. This leased line may or may not be directly connected to both the endpoints, that is router 1 and router 2. There may be a lot of routers and other infrastructure in between of the service provider, but we usually represent in a network diagram like this, because for both the endpoints it appears as if they are directly connected. Unlike LAN, which is usually 1 gigabit or above nowadays, WAN is much slower, as this connectivity costs a lot more than establishing the LAN connectivity. This is because the WAN is usually leased out from the service provider's end. Let's understand a bit of this jargon of leased line and leased circuit. A leased circuit or a leased line refers to the connectivity between two endpoints that is dedicated, just like an electrical circuit. A serial link or a line refers to the data flowing serially and that the router uses a serial interface. In the earlier days of the internet, this is how a leased line used to be delivered to the customers. It is not popular anymore now, but this is how it all began. A point-to-point link or a line refers to the fact that the link is between two endpoints only. A similar terminology for this is point to multipoint, where one point is connected to multiple endpoints. The one point is the main hub and the others are spoke. We will learn about this later in the course. As I was telling you, in the earlier days of the internet, the leased circuit or the dedicated circuit used to be delivered over serial links. These links usually had a speed of T1. That means a speed of 1.544 Mbps. This T1 terminology basically refers to the speed of the link. The WAN link or line is a generic term with no specific reference to any kind of technology. A private line is a factual representation that the data is being transmitted privately and cannot be copied by any intermediary in between. As in the last slide, I was telling you that the two endpoints connecting, that is R1 and R2, like in the diagram shown, is just connected by a single crooked line. That does not mean that they are connected directly, but in a telco environment, they can be connected to multiple hops or multiple pieces of infrastructure that the telecom operator might have deployed to make this link possible. For example, in this scenario, R1 is connected to R2 through a telecom provider wherein there are multiple switches and there are a lot of underground cabling happening in between. But for the customer ends, it appears as if a cable has been extended from one point to another point. An example of this type of leased circuit is HDLC, that is the high level data link control. As the name suggests, HDLC provides the data link protocol to the leased circuit. That is, it provides the methodology of how the frame is going to be transmitted from one end to the other end. Just like Ethernet, which uses a destination address to send the data to the correct device, HDLC also use a similar functionality. However, unlike Ethernet, HDLC is a point-to-point protocol, whereas an Ethernet is a broadcast protocol. That means when HDLC transmits data from one end, it can only go to the other end of the link. We can configure HDLC as a point-to-multipoint protocol, but we need to basically understand here is that the basic functionality of HDLC is a point-to-point protocol. This is how an HDLC frame looks like. Here the type is in a different color, as this is a Cisco specific attribute that has been added to the default HDLC protocol This attributes as the type of the frame is transmitting from one end. This is not part of the IEEE standard and has been added by Cisco. That means that Cisco HDLC is not compatible with the other vendors. Coming back to our network diagram, let's understand how the routers use this WAN data link to transmit traffic from PC1 to PC2. PC1 wraps the data in 802.3 headers and trailer and sends the packet to router 1, which is its default gateway. Router 1, on receiving such frame, discards it and adds a fresh frame of HDLC and sends it across to router 2, which is its default gateway. Router 2, in turn, on receiving such frame, discards the HDLC header and trailer and adds a fresh 802.3 header and trailer and sends the data to final destination, that is PC2, which is directly connected to router 2. So a point to note here is that the layer 2 frames that traverses through the network is not the same. At every hop and every stage that it traverses through, the layer 2 frame is discarded and a fresh layer 2 frame is added and sent across. Whether be it 802.3 header or trailer, which is the Ethernet frame, or whether be it the HDLC header or trailer, which is the HDLC frame. The operations in Ethernet WAN are very similar. The customer site 1 connects to a service provider end at a point of presence, and customer site 2 connects to the other point of presence in the other geographical location. And it appears as if the Ethernet cable from customer site 1 has been extended to customer site 2. In reality, this cable only extends from router 1 to point of presence 1 of the service provider and router 2 to points of presence 2 of the service provider. The service provider cloud is running an Ethernet emulation or an MPLS type of network, which gives the customer a false image that physically the cable from customer site 1 has been connected to customer site 2, that is from router 1 to router 2. If we see it more closely, logically this is behaving like a point-to-point link. There is a point on one end and there is a point on the other end. The packet from PC1 to PC2 traverses in a very similar manner as it did in HDLC type of network. PC1 wraps the data in 802 header and trailer and sends the packet to router 1, which is aware of the network of the PC2. Router 1, on receiving such frame, discards the 802.3 header and trailer and makes a fresh header and trailer and sends the packet to router 2, which is aware of the network of the PC2. R2, on receiving such frame, discards the 802.3 header and trailer and makes a fresh header and trailer and extends the packet to PC2 to where it is destined to. Here I would like to point once again that the 802.3 header and trailer at each of the stage is different. PC1, when sending the packet to router 1, which is destined to PC2, makes the 802.3 header and trailer, which gives the source as PC1 and destination as router 1 for that frame. Not for the packet, but for the frame. Right now, what you need to understand is that 802. Header and trailer contains the MAC information. Don't get confused if you're not able to understand it. But right now, if you understand only this part, then it is good enough. Similarly, when router 1 sends a packet to router 2, which is destined to PC2, coming from PC1, the header and trailer that come from PC1 gets discarded. A fresh header and trailer is made by router 1 and the packet is sent to router 2. This header and trailer contains the source as router 1 and the destination as router 2. A similar process happens at router 2 and the packet is forwarded to PC2. This is the case of layer 2 where MAC addresses are involved. However, when PC1 is sending the packet to PC2, IP routing is involved. PC1, which has an IP of 10.10.10.10, while sending the packet to PC2, which is 20.20.20.20, understands that the packet is destined for another subnet. Therefore, a router has to get involved. If you remember from the first video, the function of the router is to route packets between different subnets or different networks. Here, PC1, when sending the packet to PC2, understands that this destination is of a different subnet, so it extends the packet to its default router or the default gateway. Here I am using the word default gateway for a purpose as there is only one router involved and we are assuming that this is the default gateway. While going ahead with the IP routing, we will understand much more deeper concept. But right now, this is good enough to understand that this is the default route. Also note that in case of Ethernet and HDLC, the packet, that is the layer 3 information of the source IP and the destination IP, that does not get changed. Only the layer 2 information, that is the MAC address in case of Ethernet, and in case of HDLC, the source and the destination information as per HDLC gets changed. So getting back to our current scenario, PC1 is sending the packet to PC2, which is in another subnet. So it forwards the packet to its default router, router 1. Router 1, on receiving the packet from PC1, checks the destination IP address. When checking the destination IP address, router 1 checks its routing table and checks where the subnet might be routable to. On getting the information that this can be routed to router 2, the router 1 sends the packet to router 2. Same process as earlier happens with router 2. Router 2, on receiving the packet, checks the destination IP address and corresponds it with its routing table and gets the information that this destination subnet is reachable through router 3 and extends the packet to router 3. Router 3, on receiving such packet, as with all the earlier routers, removes the layer 2 information and checks the destination IP address. On checking the destination IP address, it gets to know that this IP is directly connected with it and extends the packet to PC2. Hence, PC2 gets the packet. Here we see that router 1 to router 2 is a serial link, that could be an HDLC link. Between router 2 and router 3 could be an Ethernet over MPLS link. It doesn't matter what kind of a WAN link it is. Since this is an IP routing, layer 2 information has no value here. Layer 2 information was valuable only between the two directly connected nodes, that is PC1 and router 1, router 1 and router 2, router 2 and router 3, and router 3 to PC2. As I told you in the previous slide, router is concerned only with the IP information of the packet. The IP headers contain source IP and the destination IP address. Here there are many much more fields available. We will discuss about many of these fields in the coming lessons. Right now, let's concentrate upon two things, that is the source IP address and the destination IP address. If we go back to our previous slide, the source IP address in all the IP packets remains the same as 10.10.10.10 and the destination IP address remains the same as 20.20.20.20. The data link headers are changed at every node, but the IP information is not changed. The routers get information about subnets through various routing protocols that are there in the router. And these routing protocols are the basis with which the router works. They provide the main logic of the destination IP address and the gateway through which they are reachable through to the router so that the packets can be routed. Although we can define these routes statically also, but the routing protocols update these routes dynamically and in real time as and when they receive from the other router, making our whole network smooth and scalable. There are some rules that are followed by the router while adding those routes. The first rule is that immaterial of what routing protocol is running on the router will always update the connected route automatically and will be the most preferred route. The second rule is that the routing protocol informs its neighbors of the routes that are in its own routing table, including the connected routes and routes that are learned from other neighbors also. And the third is that after learning such a route from the neighbor, the router adds the subnet to its routing table, that is, through which router will that subnet will be available is typically the neighbor router which has sent that route to the router. A very important protocol here plays a part, that is the ARP, Address Resolution Protocol, which the Address Resolution Protocol ties the IP address to the MAC address. For example, PC1 at 10.10.10.10 wants to connect to router 1, that is 10.10.10.1. The first message that PC1 sends across to router 1 is an ARP request, wherein the sender IP address is defined, the target IP address is defined, and the sender's MAC, that is PC1 MAC, is defined, but the target MAC is unknown. So PC1 sends an Ethernet broadcast asking which MAC address corresponds to the IP address 10.10.10.1, and router 1 on receiving such request sends an ARP reply. This time around it's a unicast, that is a one-to-one message, not a broadcast which is sent to everyone. And this ARP reply contains the information of the target IP address. The perspective here has changed, so the target IP now becomes PC1, the target MAC is PC1, the sender IP is router 1, that is 10.10.10.1, and this time around the sender MAC is R1's MAC. Now in future, anytime PC1 wants to connect with 10.10.1, it knows the MAC address of router 1. So it will not have to send the ARP request over and over for every message. This ARP request gets stored and gets updated time to time. Like ARP, DNS also plays a very important role. DNS is the domain name system. It acts like a phone book of the internet, wherein the domain name gets translated to an IP address. For example, PC1 wants to connect to server 1, but server 1 is a domain name. PC1 cannot send a message to server 1 directly. The computers need an IP address, which in turn gets converted into a binary number. That is how the computers communicate with one another. So PC1 asks the DNS server what is the IP address of server 1. DNS server on receiving such request replies back that hey, I know server 1, it resides on 10.1.2.3. So whenever now PC1 wants to communicate with server 1, it sends an IP packet to 10.1.2.3. Thank you for watching today. I hope that today's video was educational to you. Let me know in comments what do you think. Until the next time, goodbye.